Thank you, Professor Hu, for the introduction. A very good morning to everyone in the MEMDES conference. My name is Yu Jie, and I'm currently a PhD student working under the supervision of Professor Wang Rong at the Singapore Membrane Technology Center at Nanyang Technological University, NTU, Singapore. Today, it is my pleasure to represent my research group to present on one of our latest publications in the Journal of Membrane Science, titled Fast Water Transport Through Biomimetic Reverse Osmosis Membranes Embedded with Peptide-Attached PR Pillar 5 arenes Water Channels. This slide summarizes the outline of my presentation today. I will first start off with the introduction and research motivation of this work before discussing the materials and methods used in the membrane fabrication. Thereafter, I will link up the membrane performance with the characterization results before concluding my presentation with the key learning points. I will first start off with section 1, the introduction. Currently, freshwater scarcity is one of the most grand challenges which mankind is facing today, as it is expected to impact 4 billion people out of the world population of 7.7 billion people. And this global problem of freshwater scarcity is currently the driver for many innovations in desalination technologies. The prevalent desalination technology is seawater reverse osmosis, SWRO for short, which is a membrane-based process capable of separating salts and water. As shown in figure 1 of my slide, there has been a huge growth in the construction of desalination plants in the past 20 years, producing more than 100 million meter cube of fresh water a day, and this amount is sufficient to supply water to more than 300 million people in the world. This statistic highlights the critical importance of desalination for mankind survival, which also establishes the fundamental importance of membrane-based desalination technologies as a research topic. Currently, the state-of-the-art reverse osmosis membrane are the thin film composite type, the TFC type, that consists of an ultra-thin polyamide layer that is built on top of a porous support layer. In this design, the polyamide layer is responsible for the separation of salts and water, whereas the support layer provides the mechanical strength to the overall composite structure. Whilst the TFC membranes are state-of-the-art, empirical evidence from upper bound models in figure 2b has suggested that the TFC membranes suffer from a permeability and selectivity trade-off from a polymer chemistry perspective, which means that it is quite difficult, if not impossible, to achieve a higher permeability and selectivity using the conventional polymeric materials. This brings us to the motivation of this work, which is to design a next generation biomimetic membrane that could possibly overcome the permeability and selectivity trade-off in RO membranes. Biomimetic RO membranes typically involve biological elements or adopted concepts from biological systems in a bid to redesign membranes in bio-inspired ways. In this work, we chose the Pillar 5 arene compound as a biomimetic water channel because of its ability to mimic carbon nanotubes as well as aquaporins. And it is hoped that the Pillar 5 arene water channels can enhance the eventual permeability of the biomimetic membrane when incorporated in the form of liposomes, which are lipid vesicles. In this work, two types of biomimetic channels, the PR and PS peptide-attached Pillar 5 arene, were used in the preparation of channel containing liposomes. It is important to note that the PSPH nanochannel is a diastereomer of PRPH and is used as a negative control to the PRPH nanochannels. Now, let us take a look at the biomimetic membrane fabrication methodology. First, we incorporate the PRPH nanochannels into the lipid bilayer, and through self-assembly, the channel containing liposomes are formed. These liposomes are then blended with the MPD diamine solution, and thereafter we perform interfacial polymerization, IP, to encapsulate the channel containing liposomes into the membrane selective layer, thereby forming the nanochannel-based biomimetic membrane, NBM for short. Let us now take a look at the results starting from the characteristics of the liposomes. From figure 5a and figure 5b, we can see a rapid increase of light scattering signal within a short period of time for the PRPH liposomes, which is actually a good evidence of the fast water transport through the PRPH nanochannels. Because the PSPH channel is in negative control, the huge difference in the initial gradient between these two curves in figure 5b shows that the water transport across the PRPH liposome is actually channel mediated. In addition, we also conducted the activation energy measurements by performing the Stokes flow light scattering test at different temperatures. From the Arrhenius plot in figure 5d, it was revealed that the incorporation of PRPH into liposomes reduced the activation energy needed for water permeation from approximately 13.6 kilocalorie per mole to 8.1 kilocalorie per mole. This is another good evidence that water transport across the PRPH liposomes was indeed channel mediated. Now, let us take a look at section 5, the characteristics of the NBMs. First, we use scanning transmission electron microscopy, STEM, to observe the morphology of the NBMs. It was revealed that there were some odd-shaped features in the polyimide selective layer, and through EDX analysis, it was proven that these features actually gave enhanced phosphorus signal, suggesting the presence of DOPC liposomes inside the membrane selective layer, because the phosphorus element is not present in MPD or TMC monomers used in interplacial polymerization. In short, the results in figure 6 is actually a good evidence of the successful incorporation of DOPC liposomes into the membrane selective layer. However, because of its small sizes and low concentration, the PRPH nanochannels were not directly observed in the TEM images. In an attempt to prove that the PRPH nanochannels were indeed successfully incorporated into the polyimide selective layer, we used X-ray photoelectron spectroscopy, XPS, to compare the TFC membrane made with virgin DOPC liposomes and the NBM membranes made with PRPH liposomes. From the XPS results shown in figure 7, it is noticed that the NBMs incorporated with PRPH liposomes exhibited another unit peak at approximately 285.5 EV, and this peak is actually assigned to the ether bonds. Because the ether bonds are only present in the PRPH compound, this is actually a very good evidence that the PRPH nanochannels were indeed successfully embedded into the membrane selective layer of the NBM. Now that the characteristics of the liposomes and the membranes are discussed already, let us move on to see the performance of the NBMs, specifically the desalination performance. First, from figure 8a, we can see that as the concentration of the PRPH liposomes in the MPD solution increased from about 0 to 0.5 milligram per mil, the membrane permeability increases by approximately 15%, which we hypothesize is due to the additional free volumes created by the liposomes, as well as the water transport pathways provided by the PRPH channels. However, we also noticed that the membrane permeability did not always increase with the liposome concentration, which means that it is not necessarily true that the more liposomes you add, the permeability will always increase linearly. We hypothesize that this observation is due to the agglomeration or aggregation of the liposomes at higher concentrations, thereby forming a slightly thicker active layer that might present greater hydrodynamic resistance to the permeation of water. Moving on to the membrane performance shown in figure 8b, we can see one very important thing over here, and that is when the PRPH load in the liposomes are at a sufficient level, the corresponding NBMs showed a higher membrane permeability by about 14% than the TFC membrane made with virgin DOPC liposomes or the membrane made with PSPH mutant-containing liposomes. This is actually an indirect evidence that the PRPH nanochannels actually contributed to the enhanced permeability of the NBM. So, as summarized in figure 9 of the current slide, the enhanced permeability of the NBM membrane incorporated with PRPH liposomes was actually attributed to the preferential passage through the PRPH nanochannels in the liposomes, thereby giving water molecules accessibility to the hollow cores of the vesicles with lower hydrodynamic resistance. Now, I will conclude my presentation by highlighting the key learning outcomes of this work. Number one, the enhanced membrane permeability of the NBM membranes are attributed to the preferential water transport through the PRPH channels embedded in the form of liposomes, as shown in figure 10 in the current slide. But we also need to note that the compatibility between the liposomes and the polyamide selective layer is very important. Also, because this will guarantee the formation of a defect-free selective layer that does not compromise the membrane selectivity. Secondly, the successful fabrication of NBM RO membranes is also expected to open up new avenues for biomimetic membranes incorporating other types of biomimetic or synthetic channels, such as I-quartets or aquafudamal channels. Lastly, this work also potentially opens up an alternative pathway in the fabrication of NBMs beyond aquaporins with enhanced performance that does not come at a sacrifice in membrane selectivity. I have now come to the end of my presentation. Thank you very much for your attention. Any questions are welcome. Thank you.
Great, thanks, Ms. Lim, for the nice presentation. So due to the time limit, we just have one question, from the audience. So there's the audience ask, how to prepare the vesicles embedded the TFC membrane. I also wondering, why do you have to prepare liposome? Can you just embed the channel directly into the TFC membranes?
Oh, thanks. Okay, I got the question already. So over here, the reason why we want to put it in the form of liposomes is because we can see the water channel permeation very clearly from the stope flow light scattering test. But for pillar 5 arene over here, it is also possible to disperse directly into the membrane selective layer. But one critical question over here is that if we disperse it directly into the polyamide selective layer, we don't know if it is functioning as a filler material like carbon nanotubes, or it will participate in the IP reaction. Over here, this is not well studied yet, so we put it in the form of liposomes to make sure that it is really permeating water. We can really prove the water transport property.
Okay, good. Thank you. Thanks,
okay,
Yujie again. Let's move on for the third presentation. So is Yukun Chen here? Please turn on your video. So the next presentation is by the Yukun Chen from Zhejiang University, and we'll talk about the high separation performance in film composite membrane. So please go ahead.
Hello everyone, thanks to whose introduction. I'm Yukun Chen from Zhejiang University. My supervisor is Dr. Zhikan Yao. It's my great honor to attend this conference and introduce my recent work about high separation performance thin film composite membrane constructed by chemically inhibited intrusion of polyamide into the substrate. This work is still going on, but I'm glad to share this work with you. I will introduce my work in 4 parts, starting with the introduction. As shown below, membrane technology plays an irreplaceable role in many fields. For desalination, membrane technology has attracted more attention because of its energy efficiency, low cost, and environmental friendliness. The state of the reverse osmosis and nanofiltration membranes often adopt a thin film composite structure where a polyamide thin film is generated on the top of a porous substrate via interfacial polymerization. In a typical IP reaction, the water solution of amine monomer first impregnates substrate, followed by coating the organic solution of acyl chloride monomer to form the polyamide layer. There are many influence factors in the preparation of high-performance TFC membranes, including reaction and diffusion. There in reaction conditions, solvent, monomers, substrate, or additives can change the characteristic of the PA layer, making it unique and uncontrollable. Many previous studies have discussed the reaction factors, but in fact, the diffusion factors also plays a very important role in the formation of PA layer. In particular, the substrate which are commonly overlooked can produce expected result on TFC membrane performance. So previous studies reported the substrate containing weak reactive group hydroxyl has been improved to optimize the structure of the polyamide layer and improve the performance of the membrane at both high and low concentration. Based on the above research, we consider using higher reactivity group amino to construct the stronger reactive substrate. We investigated the variation of IP process via amino substrate and evaluated the performance of TFC membranes based on amino substrate. So let's move to the second part, membrane preparation. We adopt a common commercial PES membrane as the original substrate. The method of the amination has been reported in detail previously. DETA was chosen as an amination reagent for the porous substrate. The PES substrate was immersed in the DETA solution at 19 centigrade for hours to obtain the amino substrate. Afterwards, PIP solution and the TMC hexane solution will undergo IP reaction to form the thin and rough PA layer on this substrate. It should be noted that amino distribution on PES substrate was closely related to the amination time. Therefore, we regulate the surface amino content of the substrate by controlling the amination time. Subsequently, we used the amino substrate to conduct PA layer under different monomer concentrations to further explore the effects of amino groups in IP reaction. The third part is performance evaluation. Through a series of characterization as shown in figure, we found that the amino substrate have similar surface structure such as pore size, roughness, only the chemical composition of the substrate was different. And then we characterized the morphology of TFC membranes via TM and AFM. We found that the PA layer was more prone to cause pinholes at low monomer concentration. And at high monomer concentration, the amino group on the substrate could inhibit the intrusion of polyamide into the substrate as shown in figure. And the XPS result of characterization on the back of the PA layer shows that sulfur content increased with the amino content. This phenomenon proved that a part of amino groups on the substrate participate in the IP reaction. In order to verify the changes of PA layer, the element content of PA layer was obtained by narrow scan. We found that with the surface amino content increased, the ratio of carboxyl and amide decreased, which means the degree of cross-linking enhanced. It indicated that a much denser PA layer was formed on this amino substrate after IP reaction. The characterization of zeta potential of TFC membrane shows that the modified TFC membrane was amino substrate has a more negative charge and lower contact angle compared to the original membrane. The variation of surface charge properties and hydrophilicity may contribute to enhancing the rejection of divalent ions and water flux by means of donor effect. The evaluation of membrane separation performance determines whether the membrane should be scaled up at low monomer concentration with the increase of amino content, with the water flux of TFC membrane decreased due to the improvement of defects. And at the same time, the rejection of monovalent and divalent ions was increased remarkably. At high monomer concentration, the water flux and the rejection of divalent ions raised indicated that the enhancement of the separation performance. Meanwhile, the separation factor of chloride and sulfate also improved. In conclusion, this membrane has the best separation performance compared to others, with both higher water flux and separation efficiency. According to the result of the above characterization, we made a reasonable explanation about the possible mechanism of the amino substrate in the IP process. At low monomer concentration, amino substrate was able to enrich PIP on the substrate, thus reducing the generation of defects. As you can see on the right figure, it can be proved by the contrast of PIP absorption capacity of substrate before and after reaction. In addition, the amino groups affect the diffusion behavior of monomer, which further changes the IP process. What's more, part of the amino groups on substrate participate in the IP reaction, which optimizes the formation of the PA layer. On the other hand, the intrusion of polyamide into the substrate was weakened to some extent because of the reactive amino groups, thus enhanced the separation performance and the water flux of the TFC membrane. Finally, I will summarize this work briefly. We prepare an amino substrate to regulate the IP process for the purpose of improving the membrane performance. And the role of the amino substrate was described below. The first is enriching of PIP concentration to reduce the defect generation at low monomer concentration. The second is inhibiting the diffusion of PIP to fabricate a much thinner and denser PA layer. The third is serving as chemical inhibitor to eliminate the intrusion of polyamide into the substrate at high monomer concentration. At last, thanks our membrane group mate and thanks Professor Lin Zhang and Dr. Zhikan Yao for help advices. And this work was supported by National Natural Science Foundation of China. That's all. Thank you. Thank you for your attention. Thank you, Mr. Hu. Thank you, Mr. Zhang.
Good, great talk. You could very nice job. So I haven't seen any question from the audience, but I do have some. I saw you try to demonstrate the more monomer absorbed on the PES substrate using the QCMD, right?
Yeah.
Can you explain how to do experiments? I mean, for QCMD, it requires a very tiny amount of the substrate. So for the PES, that's pretty thick. It's much beyond the QCMD limit.
Thank you, Professor Hu. This is a very good question. And this test was we were inspired by the Professor Chu Yang Tang's group, and we just do the test. At first, we just try to we just try to indicate the PIP absorption or PIP diffusion. But when we do the QCMD, we found many questions in the test. But we this work is still going on. May we need more evidence to prove the to prove our view about the absorption, PIP absorption. So maybe we will do more tests about the QCMD.
I feel, I don't know, you know, we also do QCMD experiments, but it's really hard to work with for this purpose. You have to cut very thin slides for the substrate, and it will affect the surface property and then affect the absorption of the monomer in. But another way, you know, so you propose very thin the polyamide layer affirmed. Have you checked out the back surface of polyamide? Can you measure the depth of the polyamide grow inside the substrate pores?
Yeah. We use TM to see the intrusion of polyamide into substrate, but it's not in some extent it's not clearly, or it's not specifically about the intrusion of the polyamide into the substrate. So maybe we can do some other characterization to improve the intrusion of the polyamide into the substrate.
Right, that's an important key for your for your proposed idea. Right, but they do have some ways to characterize. Later on, we can communicate if you like. Okay, so thank you very much. We have to move on for the next presentation. Can you just log out? Great. So let's welcome our last speaker, the Miss Norman Kanhanzenda. Can you show up here? Oh, great. So we'll talk about the antibacterial adhesion performance of the dopamine cross-linked the graphene oxidal membrane. So please go ahead.
Thank you, Professor Hu. Can you hear me?
Yes, that's clear.
Okay. Okay, so just to double check that I'm on the presentation mode.
Yes, that's good. You're good to go.
Okay, so I guess we still have 2 minutes. So good morning, everyone. This is Nauman Khanzada from City University of Hong Kong. So today I will be talking about antibacterial adhesion performance of the polydopamine cross-linked graphene oxide agar membrane via in situ optical coherence tomography. So as all the other three earlier speakers already have talked about the water scarcity and the fabrication of RO and its commercial application. So I will not talk on that, and to save the time, I will directly start basically from the limitation and challenges. So despite the fact that RO membrane is widely commercialized, it still faces numerous challenges, which include fouling, which is one of the major challenges which is faced by RO membrane. So in fouling, we can characterize fouling into 3 different types, which is inorganic, organic, and biofouling. And as some of the authors have mentioned that biofouling represent somehow more than 45% of all proportion of the fouling. Another challenge faced by RO membrane is the rejection of low molecular weight hydrophilic contaminant of emerging concern, such as NDMA, boron, and other low molecular weight organic micropollutants. So which is another major limitation, which is another hot research topic these days. And the third limitation, as Professor Hu presented in her research, that the chlorine resistance of the RO membrane is another limitation. So these are the 3 existing challenges faced by RO membrane. So in this study, I will be mainly focusing on the biofouling part. And then at the end, I will also touch the second limitation because we recently have published some work based on that. So the objective of the study was very simple and clear, that we wanted to improve the anti-biofouling and also the rejection performance of the RO membrane. For that, we simply modify the surface, and for the modification, we use graphene oxide and polydopamine. If you have a question why I use that, so it's pretty simple that graphene oxide is bactericidal, hydrophilic, and for polydopamine, we use it as a cross-linking agent basically, and which is also hydrophilic, and it is regarded as a universal glue and can undergo self-polymerization, so you don't need to trigger the reaction, you don't need to provide any specific conditions, so you just give it the basic pH and then it just stick to the surface. To modify the surface using graphene oxide and polydopamine, we synthesize the graphene oxide in the lab and we use some basic characterization such as Raman spectroscopy, XPS, XRD to ensure that the synthesized material is well oxidized because we use graphite as a precursor. So from the Raman spectroscopy, we were able to check the oxidative deformation in the carbon lattice structure, while the XPS confirmed the successful attachment of the oxygenated compounds. And from the XRD, we validated that the interlayer spacing of the graphene oxide was 0.98 nanometer, which was basically increased from the graphite zone, which was 0.3 nanometer. Later, for the modification, we use a very simple technique. We use one pot mechanism. We just mix the PDA and graphene oxide. We sonicate it for a while to mix, and then we pour on the surface of the commercial membrane under shaking condition. So here you can see that the very thin layer of the graphene oxide and polydopamine layer, we use this as a PDA geo. Here, so the PDA geo layer you can see that formed. And to further analyze this coating, we use SEM to monitor physically the attachment of the GeoPDA layer over the surface, which we can see here basically. So this is the pristine membrane, this is the surface modified membrane. So the surface modification basically resulted in the appearance of the sharp edges of the graphene oxide, which apparently reduce the surface roughness. Although it's sharp, but compared with the polyamide structure, the surface, the roughness we obtained was lower. And also the modified membrane exhibited higher hydrophilicity due to the presence of the amine group in the PDA and some carboxylic group and hydroxyl group present in the GO and the PDA. We further validated the attachment of the modified layer using the FTIR. So here you can see the stretching in this zone is basically due to the attachment of the hydroxyl group and also due to the addition of the carboxyl and carbonyl groups. So after that, we ensure that the attached layer was, the material we used was successfully attached over the surface of commercial membrane. So next we investigated the bactericidal property of the membrane. So for that we used E. coli as a model bacterium, and we incubated the E. coli for 3 hours by providing the suitable conditions. So here you can see, compared with the pristine RO membrane, the surface modified membrane exhibited high bactericidal effect basically. And compared with the commercial, we obtained only 12% viability of the E. coli. So this bactericidal effect was higher than our previous study we did with the graphene oxide only, where we obtained around 70% effect using the same material and the same amount. So to validate our result, we further analyzed the sample using the confocal laser scanning microscopy, which further established that the membrane is highly bactericidal. So in the next step, what we did, we modified the membrane using the graphene oxide, simply using a spin coating method and the polydopamine. And we observed that the geocoated membrane resulted in 29% viability, which is quite in line with our previous result, showing that 71% bactericidal effect. And for the PDA, we monitored 73% viability. So from this, we concluded that this high bactericidal effect was basically the synergistic effect of PD and GO. To further monitor, we analyzed the morphology of the bacteria which were deposited over the surface. So here you can see that compared with the pristine membrane, the bacteria which was deposited on the PDA-coated surface showed the wrinkle cell membrane structure. This we ascribe this to the latent reactivity offered by the hydroxyl group and the catechol group present in the PDA layer. While for the geo, a physical disruption mechanism was observed. So together with this, we observe a very high bactericidal property from the PDA geo modification. In the next step, we monitor the anti-biofouling property, which we regarded basically as an anti-adhesion property of the membrane. So for that, we again use the high concentration of the E. coli suspension, and we use the lysogen broth as a media. So we circulated the media for the membrane conditioning, and then we replaced our feed with the E. coli suspension, which was filtered for 30 minutes to allow bacteria to deposit and grow. And then we started the filtration mechanism. So here you can see that compare with the pristine membrane, the surface modified membrane basically exhibited low biofilm formation. So in terms of the fact, we obtained 46% less biofilm formation from the PDA modified membrane compared with the pristine. And similarly, the flux decline was also lower. So after establishing the fact that the membrane we modified was highly bactericidal and anti-biofouling, so we further checked the rejection performance of the membrane against one of the contaminants of emerging concern, which was NBM, as I explained in earlier slides. So here you can see that compared with the pristine membrane, basically the membrane modified with PDA geo exhibited almost 13% higher NDMA rejection. And we regarded this high rejection to the reduction of graphene oxide during the functionalization of the PDA geo mixture. As you can see that compared with the graphene oxide, basically the PDA geo mixture was partially reduced. The oxygen content was relatively lower compared with the graphene oxide, and the XRD characterization further validated that two zones were created. So here you can see that this mainly refers to the more close to the graphite zone. So after PDA geo modification, we obtained two interlayer spacing mainly, and one of them was basically the 0.36, which was more towards the graphitic zone. So we ascribe our result that the PDA geo modification resulted in enhanced sieving effect, which mainly responsible for the higher rejection of the NDMA. So we further supported our results. In the next step, we modified the membrane. We had two different approaches. The one we used the mixed matrix approach, and in the other one we deposit the PDA and then we functionalize the graphene oxide over that. So here you can see that both the modification method resulted in different morphology. So for PDA geo mixture, we observe more like a staking of the graphene oxide layer, which we ascribe to the formation of thin PDA layer on both sides of the graphene oxide. While in case of sequential deposition of PDA and geo, we observe a thin structure of the graphene layer. So we ascribe our result that the co-deposition of PDA geo basically offered enhanced sieving effect, which were effective in enhancing the rejection of hydrophilic low molecular weight contaminant of emerging concern. We further investigated the NDM rejection for our all membranes. As I explained, that we use PDA geo co-deposition and sequential. So here you can see that compare with sequential deposition and even with single PDA coating or geo coating, the NDM rejection was higher in this case. So again, this was validating our assumption that the higher rejection was mainly occurred due to the staking of the layer, which happened during the co-deposition of PDA geo. So from these findings, we concluded that the PDA geo mixture or the PDA geo nanomaterials are effective to overcome multiple challenges such as fouling and low rejection against hydrophilic or low molecular weight contaminant of emerging concern. And the modification of the membrane basically can convert the surface into hydrophilic and can make your surface less rough. Also, From this finding, we observed that the PDA modification can also convert your surface, can give you high bactericidal effect and high rejection against the challenging contaminants. So with that, I would like to acknowledge my all research team at CTU, led by Dr. Alicia Ann, and also the University Grant Council, which supported my PhD. At the end, I would like to thank you all for the patience and listening. If you have any question, I would be happy to answer.
Good job, Norman. Thanks very much for the presentation. And yeah, so if I have any question, please type on the chat. But so far I haven't seen. But I have the question. You talk about you do the layer by layer deposition of the graphene oxide and the polydopamine. Is that correct?
Professor Wu, we did not do layer by layer basically because the main focus was the practical approach that if we are talking about the fabrication of the membrane, so it's better to have a simple mechanism. So what we did, we used the dopamine, and because dopamine to polymerize, you have to give up the basic pH. So we used the tris as a buffer. So we mixed the polydopamine amount in tris, and then we added the graphene oxide, and then we just did sonication to mix the graphene oxide layer in the suspension. So I would not call it as a layer by layer, but we did a sequential deposition, which was in the second step. So we formed the PDA layer, and then we deposit the graphene oxide. So in none of those approach we used layer by layer. It was basically the single layer.
Yeah, I just wondering, so the difference between the cold deposition and the sequential deposition.
Mm-hmm.
So cold deposition means the polydopamine modified graphene oxide, or
yeah, you can call it in this way because as I explained in the later results here and here. So basically, if you are doing the co-deposition, these characterizations are basically from the PDA mixture. We mix the PDA mixture for the same time as we use for the modification, and we characterize that material by filtering. So basically, when we mix, the PDA cause reduction to graphene oxide. For polymerization, PDA use the oxygenated functionalities to polymerize, and that basically takes from the graphene oxide. So graphene oxide ultimately reduce. So you can call it as a PDA modified graphene oxide.
Okay, thank you. Yeah, and also very surprised to see your pristine control membrane has a very low water contact angle, right? It's just about 30, 32 somewhere.
It was around 32, I guess. 32 around. We use the commercial membrane. Yeah.
For further control, you don't do any deposition, you don't do any modification. Why so low? It looks quite hydrophilic.
This you're talking about the commercial one, right?
The control membrane. You're talking about that's the commercial control where you made it yourself.
No, this is the commercial control. We've modified the commercial one basically.
Okay, so it has been modified, right?
Yeah, I guess from the supplier, I assume because it is reported that they use multiple modification as a post-treatment. So we assume that there was some hydrophilic layer.
Mm-hmm.
But we did not investigate that. What was the material basically deposited over that? It was the nanocomposite membrane.
So do you remove the preservative in the membrane? Normally they have the glycerol and some other preservative.
Yeah, glycerol, you can say, but we soak the membrane in DI water for like 24 hours, but we did not do any further treatment.
Okay, good. Thank you very much. So
thank you, Professor.
I have to conclude our session. Before that, I would like to thank all the presenters to give the very nice presentation, and thanks all the audience to join our session. And finally, I would like to remind you, join the concluding remarks. Probably you can win a big gift from the organization committee. So this afternoon, about the 13 safety, we have the concluding remark. Please join us. Thank you very much. Have a good lunch. Bye.